All right, so we're gonna explore the very simple trick. So basically, uh, we want to find ki is greater or equal to 0 instead of ki is greater or equal to 1. And so if each of these ki's are greater or equal to 1, then how do we make them greater or equal to 0? Well, we can replace each of these with some kx plus 1, where the kx uh, will represent uh, I'm sorry. Um, so we want to represent um, we want to represent this as like some kx is greater or equal to 0, right? So how do we do that? Well, we can just take one out of every single one of these. And so if you take one out, then naturally you're taking one out on both sides. You're gonna get ki is greater equal ki minus 1, or our new kx will be greater or equal to 0. So all we have to do is take out one for every single pair. So it's gonna look like this. K1 plus 1 plus uh sorry, 1 minus 1. We're taking out ones. Plus kn minus 1 is equal to k. And remember that these are the ki's is greater or equal to 1, but this entire thing will let us have kx is greater or equal to 0. Um, so yeah, that's gonna do it for us um because then now we can have a sum of kx. Um, oh, I'm sorry. This case, um, when we take this out, when we take the ones out, um, these are going to be, I flipped it. This is going to be, it's going to be ki is greater or equal to 1, and then this is going to be kx, our new kx is greater or equal to 0. Why? Because the original one had a 1 in it, right? It had an extra 1, so we replaced it with some kx minus 1, and kx minus 1 made sure that we replaced this minus 1. We did minus 1 on both sides, right? So that will make sure that we have kx, some kx, which is equal to ki, um, which is equal to ki plus 1, um, that um, that is greater or equal to 0. And so we took one out of every single one. So the new domain is going to be the new domain of, or the new range of kx is going to be greater or equal to 0 instead of greater or equal to 1, because we took one out of the ki. So now we can express this also as k1 plus k2 plus k3 plus dot 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 plus kn is equal minus n, because we have n of these minus ones is equal to k. And so now we can rewrite this k1 plus k2 plus dot 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 plus kn is equal to k plus n. And that is our home stretch. Let's use this equation, this result that we got from the previous problem, that if you have this, um, if you have this form, then then this expression obtains the number of solutions. Um, and so it turns out that this equation actually works for any uh for any for any of these k zeros, because they don't have to be they don't, like we have our new like k plus n amount of ones now, right? We're trying to separate that into uh we want to see how many solutions there are by seeing how many times they can separate into these pluses. Um, But um, but this equation also works for this one, right? Because we're still separating them into there. But now we have created our new requirement where these can be actually zeros. So even if you separate the plus signs into these plus signs, uh, there are some that can be zero. So we're successfully making a group of zeros using the result we got from last time, where it had to be ki is greater or equal to 1. We have the same forming equation um, in which that works. So um, so now the new range would be greater or equal to 0. Um, yeah. And so each of these will indeed work. And so our formula for this, for the number of solutions is k minus 1, k plus n minus 1, uh, and still n minus 1. All right. And so that is equation 1.4.2. Um, and notice that that is also equal to n plus 1 minus k plus n minus 1. Choose k because there's actually a symmetry. Um, there's a symmetry property between choosing. So those are just natural equals. So it just works out. And yeah, this method is called stars and bars because when we want to like groups, we use the plus signs as like bars for these groups. And each of these each of these ones that we use that we separated them, we could use them like as stars. Um, but there's also other ways to do it to obtain this result. Um, Notably, uh, you can you can say like um, you're basically having the same thing as like permutations, right? You're you're using n elements and you want to choose you want to choose k elements with repetition. Um, you're separating them into groups. Remember the relationship between permutations. You have p and k is equal to number of groupings um, divided by number sorry multiplied by the number of arrangements. And remember that this was k factorial. This was uh, c and k, and that was previously what we found. But now the number of arrangements we aren't sure of. But using our equation that we got, this equation, uh, how do we solve that in this similar fashion? Well, it's basically finding how many ways we can like uh we still want to find the number of groups, right? Because we're trying to find unordered sequences. Um, but the number of arrangements will be different. Uh, P and comma K is still the same because we're arranging um we're arranging basically um K amounts of uh K plus n minus 1 amounts of objects, right? We have K yeah we have so let's look at this. Look at the left side. You have you have n groups and then you're using K objects total. Your job, our job is to put this in that. Um, but these n groups are separated by n minus one bars, which is just the plus signs, right? So if you have n minus one bars, um, and you want to see how many, k objects can fit in those, uh, so you're actually not putting into, you're trying to put it into n groups, but to do that, you try to see uh, how many, how many ways to put the objects into the n minus one bars. So you have k objects, n minus one bars. And so this is your total amount of objects. And so there's two ways to do it. Um, one way to think of it, like you have this, right? You have to follow that, you have how many permutations to use this, and you're choosing um um n minus one bars. Like you want to get it into the form of like some star, star, bar, star, star, bar, bar, star. So you want to get into like this, and there are going to be k stars, and you have n minus one bars. And that's taken from like both sides. You have k objects, you have k like ones, and you have n minus one bars that you're separating into. And so that's the total amount of objects, and we're basically counting how many ways to distribute that uh, into this form. And so we can think of that as like what is the total amount of arrangements? Well, it's just n plus k minus one. Uh, we're doing that choose itself, right? I mean, permutate itself. Okay, and that is also just that's equal to n plus, like this is the total amount arrangements, total total arrangements, and so you have n plus k minus one arrangements. You have that factorial by definition, and you have that minus that factorial, which is just zero factorial, is equal to n plus k minus one factorial. So following this equation, you have how many total arrangements. You have this amount of n plus k minus one total amount of arrangements. And so let's represent the total amount of groups and as like x, right? And then let's see how many arrangements can be formed, like how many symmetries, uh, like indistinguishable objects per group. Like this is like one grouping. How many times can you switch the bars or the stars to obtain the same thing? Well, all the stars are indistinguishable, and all the bars are also indistinguishable. And so what you can say about that is, since you have k stars, um, you have uh, you have k factorial amount of arrangements in that, right? Why? Because that's also p of k comma k amount of total arrangements that you can make for the stars, right? To see how many times it can be switched around in the same spots. And so that's going to be equal to, if you evaluate that, that's equal to k factorial. And that's the same thing for the bars. Number of bars, like in this case, if it's just 3 bars, then you can switch it around 6 times. You have this bar can go here, only them two switched. You can switch these two. You can switch all 3 of them. There's going to be 6 ways to do that. And it's evaluated by p n minus 1 comma n minus 1, which is also equal to n minus 1 factorial. And so this is also equal to x is the x is equal to n plus k minus 1 factorial over k factorial times n minus 1 factorial. And this is indeed equal to the other, uh, this binomial coefficient that we got. We have k plus n minus 1, choose k, which is also equal to the k plus n minus 1, choose n minus 1. And so that's another way of doing it. And the last way of doing it is like when we were at this stage, we had k objects to choose from, k like ones to choose from, and then we want to see how many how many ways to separate them into the bars, because like I know like we basically want to um separate them into the plus signs, but um like we want like we have we have k objects, but we also have k minus 1 plus signs. But if you want to account for the 0, you need to account uh for when you have 0 items with 0, right? Like the groups with 0. And so it works out that if you have k objects, you arrange them into n minus 1 bars, then it works. And so if we take this example, another way of doing it is think of like the stars as one group. So if the stars are one group, then and the bars are another group, then you're basically trying to choose from the total number of objects, which is n plus k, k plus n minus 1 total objects, into a group of k stars. So how many ways to distribute that into k stars? Well, that's just k plus n minus 1, choose k. And you can also say this, after you choose this for stars, right? After every star is chosen, then like you're gonna have k plus n minus 1 spots. And so these are all filled. And so, I mean, sorry, they're all not filled initially. And then you choose the spots for stars, then the rest of the spots will automatically be chosen uh, for for the bars. And so this gives the total number of ways itself, and you can also do this for n minus 1 bars. So if you choose a bar first, that also works, and that gives us the symmetry that we got here. All right. And so yeah, that's stars and bars. Let's look at that example. All right. So this is our final table that we got, that we filled in our original table. And so now you want to distribute 6 tablespoons of sugar into 4 different bowls with various ingredients. Uh, bowls can hold different amounts of sugar, including 0 tablespoons. And so how many ways can you distribute the sugar amount in bowls? Well, that's just the equation that I got earlier, right? For the multiplicities. But instead of k multiplicities, we have I mean, sorry, instead of n multiplicities, we have 4 multiplicities that we want to, like, we have 4 groups that we want to separate this into. So we have like just like from last time, we have k1 plus k2 plus k3 plus k4, and this represents 4 groups that we're separating it into, and they all add up into 6 tablespoons of sugar. And we want to find where ki is greater equal to 0. Well, that's our stars and bars formula, right? So what's the answer? Well, k plus n minus 1 over n minus choose n minus 1. In this case, the 6 is k and the 4 is the n. And so you have 6 plus 4 minus 1. Sorry, not divide. And then you have n, you have 4 minus 1. 3. 9 choose 3. Uh, this is 9 factorial over 3 factorial times 6, 9 minus 3 factorial, which is 9 factorial over 3 factorial. over 6 factorial is equal to 9 times 8 times 7 times 6 factorial over 3 factorial times 6 factorial. The 6 factorial cancels out. The 3 factorial becomes 3 times 2. And that cancels with the 9 to get 3 on top. But 2 cancels. You get 3 times 4 times 7 is equal to 12 times 7, which is 84. All right. And so, yeah, you have 84 ways as your final answer. And that's the application of searching bars. All right. Have a nice day.